Charge Q is to be distributed on two conducting spheres. The total charge here is capital Q. What should be the value of the charges on the sphere so that the force between them is maximum? Now I don't have to discuss about the repulsive force because since it's the same charge that has to be distributed across the two spheres, then definitely the force is going to be repulsive when they are placed at a fixed distance from each other in air. So here main assumption you need to take here initially when you're starting out here, the fixed distance, you know what, let's just take the fixed distance as r. Oops, just trying to activate my pen here. So the fixed distance, we're going to assume that we are going to keep that fixed as r, and we also know that the total charge is actually q, right? So q1 is, if q1 is actually small letter q, then the value of q2 is capital Q minus q, since the total charge here is q. Therefore the force of repulsion between them is going to be k into q minus q multiplied by q whole divided by r squared. And this relationship is pretty much straightforward because you can only multiply it with the magnitude of the force. So we'll just simplify this equation, kqq by r squared minus kq squared by r squared. Now here's where it's interesting because for you who, I mean, maybe you might not have covered mathematics at this point, but if you have covered mathematics at this point, right, then the next step should be pretty much logical, because when the maximum of an equation is to be calculated, right, there are two ways that you can approach it. You can find the first derivative, which is df by dq. Remember, we have to maximize capital Q here, so capital Q is the term to be chosen for differentiation. That means the total charge should be chosen for differentiation, which means ultimately there's going to be only one term left at the end after all the differentiation is taking place, which is going to be kq by r squared, while the other term on the right side is going to go all the way to 0. That's how simplified this problem becomes at this point of time after you take the differentiation at this point. So let's now see here. If we have differentiated df by dq over r squared, now the condition for maximum is that df by dq, now if I can't take a second derivative here because this goes to a constant, right? Well, in this case, if I do take the second derivative and I'm not getting a value 0, right, here you can see that it does not fulfill the condition for a maximum. So in fact, I should in fact be differentiating df over d small q to get the answer that I desire. So kq over r squared minus 2kq by r squared. Now it makes total sense. Now the differentiation that I've done makes total sense, and now I'm at a position in which I can finally evaluate the maximum condition, because here a second derivative exists and the second derivative d square f by dq squared is less than 0. Therefore there is a maximum available for this problem. So there is a maximum possible here in this equation. So now I am going to find out the value by simply equating df by dq equal to 0. So that's the main reason why here, if you know that you cannot differentiate this equation with respect to q because no maximum exists for the function. So I'm just going to write that down here, no max. Yeah. And now moving on to the next page, so we will just equate our equations. Kq over r squared is equal to 2kq over r squared, because we are evaluating the condition df by d small letter q is equal to 0. Now that we have an equation, we'll just cancel out all the terms and we're just going to get the final answer. Capital Q is equal to 2q, which means twice the charges are going to be present over there. That means the charges are equally distributed. So q1 is equal to q by 2 and q2 is also equal to q by 2. Therefore the answer to the question here is that the value of the charges on both the spheres, they must be equal. So the charges must be equal so that the force of repulsion to be maximum. So charges equal for maximum force, and that's how you logically solve this equation, and you also verify which q to be differentiated. Thank you.